On February 4th at 4:37 p.m. local time, the towering Mount Mayon volcano unexpectedly erupted, producing a notable explosion and sending superheated pyroclastic flows down its southern slopes. While this type of activity is fairly common at certain volcanoes such as Fuego in Guatemala and sometimes Sakurajima in Japan, some observers might be perplexed as to how Mayon actually produced an eruption. After all, it produced a 5.5-month-long eruption during 2023, which ended around November 30th. No lava flows occurred since, the amount of gas emissions Mayon produced greatly decreased, and the number of volcanic earthquakes returned to a weekly average just barely above zero. Yet, I believe that the 249-second-long eruption which occurred was completely phreatic in nature, and the entire sequence, including its pyroclastic flows, originated due to an aspect of the area's weather. Specifically heavy rainfall. During Mayon's 2023 eruption, I had observed that days with higher levels of volcanic earthquakes correlated strongly to days where it happened to rain. But I also observed that occasional ash-producing phreatic explosions were seemingly linked with periods of heavy rainfall, specifically involving days where more than 1.5 inches or 38 millimeters of rain fell. Explosions would either follow A. within 24 hours of the heavy precipitation event, or B. sometime between 7 and 10 days later. In the case of Mayon's February 4th, 2024 explosion, scenario B is what occurred. I can attribute it to a heavy rainfall event on January 25th when approximately 4.5 inches or 11.4 centimeters of rain fell, representing the volcano's heaviest rainfall in a single day in a little over 2 months. My hypothesis is that around 1.5 inches of rain is needed to saturate the ground, causing water to pool and then seep deeper into the ground. Within the next 7 days, groundwater from the recent rains seeps into Mayon's still hot magma conduit. While no longer erupting, many lava flows can take several years or even decades to fully cool, so the groundwater can be encountering hot rock at temperatures upwards of 500 degrees Celsius. Some of the heat from the solidifying magma subsequently transfers into the water, heating it and causing it to flash to steam. Since the same mass of steam takes up about 1,600 times the volume of water it once was, this reaction causes an immense amount of pressure to build. Eventually, a sufficient quantity of steam becomes pressurized just enough that it actually fractures adjacent rock, causing it to escape via a path of least resistance which happens to be upwards in a phreatic explosion which does not eject any fresh lava. In other words, while it truly is possible that the latest eruption of Mayon was caused by a fresh batch of shallow magma, its geothermal sensor readings suggest a non-magmatic cause. While more explosions could occur in the next few hours to days, it is unlikely that any will reach the same intensity of the 4:37 p.m. eruption, which generated a plume of ash that rose 1,200 meters above Mayon's summit. Luckily, no one was harmed by Mayon's latest eruption, as there is still a 6-kilometer exclusion zone in place, and the pyroclastic flows it just produced traveled no further than 1.8 kilometers downslope. While cooling magma retains the potential to produce similar explosions, it is unlikely that Mayon's exclusion zone will be reduced anytime soon. Looking back at the explosion which occurred, you can identify isolated ballistic blocks of material which were launched high into the air before falling back to the ground. These fragments represent blasted portions of Mayon's 2023 summit lava dome. I estimate that the singular explosion ejected around 14,400 cubic meters of ash and pyroclastic flow deposits, meaning the February 4th explosion just barely passed the threshold to be assigned a Volcanic Explosivity Index of a 1. As a final note, I would like to thank my new patron John Mundy for supporting this channel.